Okay, so I got my notification. I'm just going to check and see if I can hear, see what it's looking like. So we were able to connect. We should be live. I'm opening it now just to make sure the audio is working properly. Okay, so we got a confirmation on the audio, so I'm going to let that be. Okay, so what this is, today, what we're doing, so I realized that one of my students brought to my attention that the last few sections that we have, I didn't have video recording. So what I'm doing, I'm going to go ahead and do the video recordings for the last few sections, so that way they'll be on file, we can use them in the future. So today we want to take a look at this. Now the formatting is different. I know what I can do. Let's go like this really quickly. Hopefully it won't distort it too terribly much. I think that'll be okay. All right, so then for us, we can't worry about that right there. And let me open it here. Okay, so I'll let that be, and I'll just kind of keep checking it. So if you're just coming in, we are actually streaming live on YouTube right now. So what that means is just picking up the audio, and on YouTube we should only be able to see what we see on the screen here. So I just want you to be aware of the noise is the microphone is very sensitive, so unless you want to be recorded on YouTube, you might want to kind of monitor your volume today. Quick snapshot of the calendar. So today is the 18th. Let's see. So a week from today, we want to take exam 3 over everything that's after chapter 2, right? So after exam 2, should I say? So a week from today is exam 3. We're going to have video recordings for the remaining sections, so you're going to have to watch those on your own. Take notes if you're in class. Email me or contact me if anything is not clear. We want to do the homework associated with each section, and let's just knock it out. We're also going to be on the lookout for a study guide, right? So the exam 3 is going to be the 25th, a week from today. Same kind of deal as before. I make a study guide. That takes top priority. So at first glance, you want to be comfortable with everything on the study guide. And that's the top priority. Once you're comfortable with the questions on the study guide, then we're going to move into go back to the homework, right? So, but that's kind of how that goes. And then the final exam, I think for us, is going to be September 30th, so that Monday, right? So this is why we're kind of having to do things the way that we're doing it. Okay, I can't think of anything else. Any other questions before we get into it? Okay, can I Zoom or something? No? No? Okay, I can't get them to behave the way I want. I'm gonna let it be. Okay, so if there aren't any other questions, I feel like this is okay. Everything looks okay, so I'm gonna let it be and just move forward. Okay, so again, we kind of have to skip a little bit. I have section 4.1 and 4.2. 4.1 is already loaded to YouTube. 4.2 I recorded just a few minutes ago before I was working with you all. So I have the video. I'm just going to load that video to YouTube. You're going to have to watch that on your own, take notes as normal. So what we're going to do right now, we're going to start with section 4.3 logs, and I'll try to clear up anything that might not be clear that popped up in exponentials. Can somebody explain to me, we talked about inverses. What do we mean by an inverse, given a function? What is the inverse of a function? Anybody remember that? So remember last time, say we wanted to find the inverse of a function. Say we had y equals 5x plus something. How do we find the inverse of the function? Switch the what? We switch the x and the y and then what? Solve for y, right? Say we have our original function and we have the domain of the original function and we have the range of the original function. Can you tell me, given the inverse, if we know the domain and range of the original, how does that relate to the inverse? The domain of the original is the it's basically the opposite, right? The domain of the original is the range of the inverse function. And the range of the original is the domain of the inverse. So the reason I'm bringing this up, because logs are actually the inverse of exponentials. An exponential function is a function where the variable is in the exponent. So you have to watch that video to see how that goes and some notions there. We're going to kind of continue the discussion here, and we'll try to keep it as clear as possible. So, and I'm going to bring one other idea up. The graph of an exponential, can you explain to me, if I were to say a horizontal asymptote, what does that mean, a horizontal asymptote? So in the long run, what happens? If we have a horizontal asymptote, it gets what? As far as the asymptote is concerned. If this is the asymptote, what's going to happen with the function? It's going to get what? Really, really, really close to the asymptote. So an asymptote in the horizontal sense is going to be this line that the graph, in the long run, it's going to get really, really close to this line. It's going to get really, really close. So exponentials have this horizontal asymptote. They start off really close and they take off like that. So we're going to use the inverse property of that to talk about logs. One other question. Given the graph of the original, how do we get the graph of the inverse? Anybody remember that one? Yes, rotate about what? So we do, it is a mirror image about a line. So given the graph of the original, the graph of the inverse, we're going to rotate about the line y equals x. If we just switch all the x and y coordinates, we're going to get a mirror image about the diagonal line y equals x, right? So that's what we needed to kind of introduce into this. So let's take a look at it and see how it evolves. So again, now we didn't talk about this together. You're going to have to go back and watch the video for this part. But an exponential function is what you see here, right? That part there, where we have some y equals a to the power of x, where a is just some number, real number, and the variable is now in the exponent, right? So, you know, you have to kind of go through that, and we'll kind of take it step by step as it arises. And yeah, so we'll kind of let that be. Okay. Okay, so remember, so now, if the exponential function is of the form y equals a to the x, and we said to generate the inverse of a function, we switch the x and the y's, so then the equation that we see at the bottom, notice that the x and the y switched. So the equation that we see at the bottom is, it's okay, just hit the button, yeah. The equation that we see at the bottom is the inverse of the exponential, right? So this is how we're going to introduce the concept of what we mean by a log. Okay, so right now we're going to explore the inverse of an exponential. Okay, I'm going to let that be, okay, right here. So let me kind of say this really quickly. So the exponential form, we have y equals a to the power of x. When we go to find, so let's do it like this. So say, come on. Let's just clear the ink. And let's change this to this. Okay. So say our f of x was a to the power of x. Okay. Let me think about it. What was I about to say? Yeah, I know, but I'm trying to think. There was something else I wanted to mention. Okay, so if we wanted to go to find the inverse, we would have y equals a to the power of x, and we said we're going to switch the x and the y, right? So then the inverse function is going to be x equals a to the y. So this is going to be the exponential form of a log. If we wanted to take this form and write it as a log, what we do is the base swings and becomes the base of the log. So this is actually equivalent to log of x base a equals y, right? So that's what we see at the bottom here. If we have y equals the log of x base a, that's true if and only if, to convert between the log form and the exponential form, the base swings, right? If we swing that base a over to the left, then it's going to be a to the power of y equals x. And vice versa. If we want to go from the exponential to the log form, the base a will swing. Let's work a few examples and it'll make sense, right? So this is just a brief introduction. I think I'm going to leave those markings there and let's kind of move forward. All right. So for instance, let's start with the exponential form. 2 to the power of 3. What does that mean? If we said 2 to the power of 3. 2 cubed means what? 2 times 2 times 2, right? So 2 to the power of 3 means 2 times 2 times 2, and the answer is 8. Now, if we want to take that exponential form and write it in log form, what's the base on the right-hand side? If we have 2 to the power of 3, what's the base? Base of 2, right? So the base is the red 2. If we want to write that as a log form, that base is going to swing to the other side. So if we swing that base over, then in exponential form, this is actually the same as the log of 8 base 2 equals 3. Okay, I give extra credit for this next question. I give extra credit for this next question. So if we look at that first line, we see that it says the log of 8 base 2 equals 3. So this is an extra credit opportunity. In any calculator that can do logs, not the advanced calculators, but in any calculator that can do log, how would we put the log of 8 base 2, how would we put that in the calculator? Any calculator that can do logs. So that's why I leave that as extra credit. Oh, do I need to reload this? There we go. Thanks. Go ahead. Oh, so yeah, so maybe in that one you can adjust the base. So with a log, does anybody know the traditional base of a log if we don't identify the base? That's 10, right? So for a common log, which is what we see, the common base is base 10. But in these, we've identified the base. So if we just hit like log of 8, that's going to be base 10. So there's this thing called the change of base formula. So if we want to do the log of 8 base 2, in any calculator that can do log, we would do the following. So we would say log of 8. Again, if we just hit enter, that's not going to work. The way we use the change of base formula, we would say divided by the log of 2, right? So then when we do that, that gives us our desired result. So the technique that you just saw me do, that's called the change of base. So that's why I just wanted you to be aware of this. Oh, you guys can't see it. Deck on it. So let me kind of show you what I mean. I'm gonna go like this. I know it'll switch over. Okay, so what I did here, I said the log of 8 divided by the log of 2 because the base was 2. So then it gave us our result. So again, log by itself has a base 10, but to change the base, we can say divided by log of 2, right? That's why I made that extra credit. That's coming up. Okay, so because yeah, because the whole point was it was supposed to be in any calculator that can do log. Yours is an advanced calculator, so all calculators can't do that. But if your calculators can do log, it can use the technique that we just described. So the reason I bring that up, because we have these expressions on the left, we can actually just put those in the calculator, right? And we can verify all of these numbers. For instance, in that second line, we have the log of 16 base a half equals -4. How would we put that in the calculator to check, to produce that -4? So on the second line, we have the log of 16 base a half equals -4. Log of 16 divided by the log of 1/2, right? So if we did the log of 16 divided by the log of half, we should get the -4, right? Just test it out a few times. Log of 2. Yeah, log of 2. That's okay. Okay, so we'll work a few examples converting between log form and exponential form. But this is just a quick little something here. So let's see if we can get an example. Go ahead. So keep in mind, this is already on Moodle. You actually already have access to this. Okay, I don't mind if you take a picture of this as well. I don't mind that. All right, so let's look at this. So it says to remember the relationship between a, x, and y and its forms, refer to these diagrams. I'm going to kind of let these be. I want to just work an example. So y equals the log of x base a. And then notice, if we swing the base to the left, then we have a to the power of y equals x. So these two forms are the same. They mean the same thing. It's just one is in log form, and the bottom one is in exponential form. But these are going to give us the same results because of how we did it. Let's, yeah, this is fine. Okay, so like in this one, we're asked to solve equation, right? So what we're going to do, we're going to write this as an exponential. Let's start by getting a copy of the original. So we're here, right? So here is the original. Oh, nope, nope. Let's go. Let's clear the ink. I'm not used to this system. Okay, there we go. So here's a copy of the original. Log of 8 over 27 base x equals 3, right? So now, if we wanted to write this as an exponential, how we go about that? What's going to swing? What's the base in this case? The x is the base, right? The base of the log, so that's going to swing to the other side. No, I'm just going to swing it over. I'm just moving it from one side. So we're going to rewrite this log as an exponential, right? So when we do this, we'll get 8 over 27 equals x to the power of 3. Is that okay? 8 over 27 equals x to the power of 3. So now, if we have x to the power of 3 equals 8 over 27, how do we get rid of that 3? Take the what on both sides? Okay, let's do this. Yes. Everybody hear that okay? Is that okay with everybody? I heard take the cube root on both sides. Is this okay? For instance, so we're going to do like this. Is this okay? So the log went away because what we did is we rewrote the log as an exponential. We just swing the x to the other side. So the base of the log became the base of the exponent, and these are essentially the same. Yeah, this is just writing the same thing different ways. Yeah, once we swing the x over, then we're at that last line that you see, right? If we take the cube root on both sides, then we're going to get x equals... Now, we can rewrite this as the following way. Cube root of 8 divided by the cube root of 27. What's the cube root of 8? What times itself 3 times gives us 8? Does that make sense? 2, right? So the top is 2. Tell me about the bottom. So 3, right? So we're saying that x equals 2 over 3. Okay, so the top is 2 because 2 times 2 times 2 is 8. The bottom is 3 because 3 times 3 times 3, 27. 27, okay? So we're saying the answer is x equals 2 over 3. Now, how can we check something like this? Plug it in for x. Okay, so if we plug it in for x, let's do that really quickly. So let's go like this. And we want to do a quick check. So we're going to say check. Okay. So we're saying that the log of 8 over 27 base 2/3. The question is, does that equal 3? How can we check something like that? Okay. Log of 8 over 27, right? Log of that divided by 2/3. Is this okay? It should, if you put it in a calculator, it should give us a 3, right? Let's just take a look at it since we have it right here. So let's see. So let's do the log of 8 divided by 27. This definitely takes practice because if we type it in wrong, we're going to get a wrong result, right? What did we say? Log of 2 over 3. And what should be the result? 3. And we get it. No, I did that. I did that because most people don't know that. Sometimes students know it, so that's why I throw it out there. Okay, but let's kind of keep going with the flow and we'll see how it goes. Any questions here before we go forward? So this is kind of a little bit loaded, but I think we kind of made our way through it. Okay, can I get to, that would be nice if I could keep that, but I'm gonna just go ahead and clear these images. Oh, it's not gonna let me clear it now? Okay, maybe it's not going to let me erase either? Okay, I see what you're doing. Okay, well, when I go to advanced, it's going to kind of overlay, so I can't get that one to go out. I think we solved that one, right? We finished this one out. Let me see. Oh, yeah, they're doing a check. So they're plugging it in. So now when they went to check, they replaced the x with the 2/3, but then they rewrote the log as an exponential. So they swung that base to the right. So then we had 2/3 to the power of 3 equals 8 over 27. And then you see it checks out. The left equals the right. Thank you. Okay. So let's just try another one. Let's try another one. Okay, solve this equation. So given something like this, where does your first mind go as far as what to do? So move the base. Yeah, move the base. What you're saying is correct, right? Right? What were you saying? Yeah, that's right. That's okay. So let's move the base to the right. We're going to rewrite this as an exponential. So when we do this, we're going to have what? 4 to what power? 5 over 2 equals what? Equals x. I think so, right? Okay, now, if we have 4 to the power of 5 over 2, here's a refresher. What does that denominator of 2 mean in the context of the original? So when we say to the power of a half, what does that mean? Okay. If we had, let's do like this. If we have, what does x to the power of a half mean? What if we had the cube root of x? What does this mean? How do we write this as a x to the what power? Remember before we said the index was the what of the exponent? Instead of the third, x to the x to the power of 1 over 3. 1/3. All right? I think before we said that a denominator in our exponent is the index of the radical. Right? So x to the power of a third is the cube root of x. So then if we have x to the power of a half, what is that going to be? Okay, let's do this. Let's do this. Say we said the fifth root of x is the same as x to the power of what? 1 over 5. So then x to the 1/2 should be square root, right? X to the 1/2 is the square root of x. All right, I think we mentioned that before. No? Yes? Okay. So if x to the 1/2 is the square root of x, let's go back to our number. Let's go back to our number. Right? So this 4 to the 5/2, we can rewrite it as 4 to the half to the power of 5. Is this okay? Is it safe to say that 5 times a half is 5/2? Okay. So then if we say 4 to the power of a half, what does that mean? Square root of 4, right? Let me see something. Right? So when we have a fraction and exponent, again, the denominator is the index of a radical. What's the square root of 4? 2. So then x is going to be 2 to the power of 5. What's 2 to the power of 5? 2 times 2 is 4 times 2 is 8 times 2 is 32 is right? So 2 to the 5th should be 32. Let me think about this for a moment. You see the screen? The last line? Is that okay? But wait. I'm trying to think. Wait. Yeah, 32, right? Because we wouldn't leave it as 4 to the power of. We can actually simplify that number. Let me make sure that I got this correct. Hang tight. Yeah, we just simplified it all the way down, right? 32. Yeah, this is okay. It actually kind of lined up. So what if it was 3? What if it was 5 over 3? So then it would be the cube root of 4, right? Then something like that we probably would leave because it's no perfect cubes. Let's try another one. I'm going to leave this actually like it is. Okay, so let's try this one. So if we were to do the same thing. So we have log base 49 of the cube root of 7 equals x, right? Actually, let me think about it. Yeah, let's write this. Let's solve this without a calculator. Now we could use a calculator to jump straight to the answer. Anybody? I'll give extra credit to the first person. If you give me the answer immediately, I'll give you extra credit for that one. Did we start in attendance? You have the answer already?
I have the answer.
Wait, I saw her here first. Anybody else need to sign the attendance? Ladies first. Go ahead, Miss Wilson. What did you have? Okay, did you get this? You got a different result?
Yes.
You got a different one? Okay, so this is Miss Wilson. Mr. Wardrobe, what did you get?
0.532. I got a different answer.
Okay, wait. You got 0.5323?
I got a different answer.
Wait. Mr. Wardrobe, right?
Yes.
Wardrobe. I'm probably spelling that wrong.
WORJROH.
JROH. Okay, instead of a D, I put J. I got you. Let's go like this.
Wait, I just said my last name on the.
Yeah, I know. I'm trying not to. It'll be okay. Wardrobe. Okay, I can't spell today. Sorry. Okay, let's test this out. So, let's try to solve this without a calculator. Did somebody get an answer other than this? You got 1/6? Okay, that's on the board. Okay, let's see how do we do. So, let's write this as an exponential. So if we go to write it as an exponential, what happens? What swings? So the 49 swings to the other side, right? Let's see what happens if we do this. So we're going to get, what? 49 to the power of what? X equals what? Cube root of 7, right? Now, the goal here, can we get these two to have the same base? I'm going to introduce a property to you. But the first goal, let's try to can we get the left and the right to have the same base of the exponent? What base do you think we can get these both to be? Can we get them both to be to base 7, right? 49 is what? 7 squared. So let's rewrite that. So 49 is 7 squared. We're going to leave that x there, right? We got the cube root of 7. That's the same as 7 to what power? The power of 1/3. Okay, the third is fine. So then now, when we say a power raised to another power, what do we do with those two numbers? Well, before that, we have the 7 squared to the power of x. What do we do with that 2 and the x? We say a power to another power, so we multiply, right? 7 to the power of 2x. So then that result is going to be 7 to the power of 2 times x equals 7 to the power of a third. So then now, what we mentioned in the last section that you all are aware of, in order for these two exponents to be equal, in order for these two expressions to be equal, the exponents have to be equal. So what we do from this point, all we do is say, this is only true if and only if 2x equals a third, right? So now from here, what do we do to solve? Divide both sides by 2, x equals, if we have 1/3 divided by 2, we do what technique? Keep, change, flip. So this is the same as a third times what? Instead of 2, third times a half, and what's that result? And the points go there. Where's my attendance?
So you ignored
The 7, yeah. So, yeah, I can't. You got to bring it because I'm kind of tethered. I got my microphone. It don't work like that. It don't work like that. That's okay though. Well, okay. So yeah, okay. So let's see if we can do this in the calculator. Okay. So let's see what happens if we do this in the calculator. We got cube root of 7 base 49, right? So we would say what? The log. Now, how are we going to put the cube root of 7 in the calculator? Okay, I'll give extra credit for this question. How do we put the cube root of 7 in the calculator? 7 to the power of?
3.
He got it. He got it. You said 3. She said 3.
That's the same thing.
No, it's not. No, it's not.
It is. The cube is a 3.
Those are reciprocals. You were close. Close but no cigar. Close but no cigar.
He the one who heard me say this.
Y'all said it simultaneously. It was like, just like that. All right, we got this one right here. Miss Ingram, okay. Plus 1. And not Hawkins. Where is it? Hammond, right? Okay. I got you, Miss Wilson.
What about the person who gives the answer 1.5?
Okay, so let's look at we gotta keep it moving. Let's keep it moving so that we can try to get these points out. Okay. Where did we leave off? Okay, so let's see this in the calculator. So 7 to the power of 1 over 3. That's not right. 1 over 3. Okay, so we close off that log. We said divided by what? The log of what? 49? And we should get a, what answer did we get? We're going to hit math as a fraction. And we get our 1 over 6. Let's hit math as a decimal. Okay. Well, so let me see. Right here, that's not what you gave me earlier. Discard. Okay? I think I just discarded it, so you got a little bit lucky, but oh no. But what other one? We got to keep going. Like if we keep stopping, then there's less chances for us to get it out. Okay, let's kind of keep going. So we got this result. We're gonna just go ahead and advance the slides, right? So we swung the 49. We got 49 to the power of x. How many slides altogether? Oh, we got a good ways to go. 49 to the power of x equals the cube root of 7. We just did this. 49 was 7 squared. The cube root of 7 was 7 to the third. Then we get this. Then we equate the exponents. Then x was 1/6. All right, so this is what we had written out, but now we see it typed out. Okay. Hopefully I'm not strictly positive and not equal to 1. We call this a log function with base a. So the blue that you see to the right is the graph of the log function. If we were to rotate this graph about the line y equals x, that red graph is actually the graph of an exponential. The red graph has this property, has this aspect or characteristic we call a horizontal asymptote. So the x-axis serves as a horizontal asymptote for the exponential function, which means that as we go off to negative infinity along the x-axis, the red graph gets really, really close to 0, but it's not going to cross it in this case. And then once we rotate about the line y equals x to generate the inverse, the blue is the graph of the log function. The log function has a vertical asymptote. So that means as we go off to negative infinity along the y-axis, it gets really, really close to 0 coming from on the right-hand side of 0, but then it goes off to the right as you see. So the blue is the graph of the log. The red is the graph of the exponential. All right? Okay. So we're going to kind of just let those images sit for just a moment, and let's kind of advance. Any questions? Let me pause for the cause. Any questions here before we go forward? There should be questions. There should, but it's okay if it's not. Okay. Okay, so let's move forward. I'm going to let that be. Okay, so really quickly. Oh, darn it, it's there. Okay, looking at the graph of the log, which is the blue graph, what's the domain, the very left to the very right? How far left does the blue graph go? How far left does it go along the x-axis? The blue graph, not the red graph. Okay, does it go to the left of 1? Like, for instance, when x is a half, can we find a value on the blue graph? So how far left does the graph go? If there's a vertical asymptote on the y-axis, what's the far left of the blue? All right, can it go further to the left? How far left? 0. It gets really, really close to 0, but what? We don't include 0, right? So for the blue graph, the far left is 0. What's the far right? How far right does the graph go? Infinity, right? Okay. So the domain is 0 to infinity. How far down does that graph go, the blue graph? Negative.
Infinity.
It goes down to negative infinity. How far up does the graph go?
Positive infinity.
Is this okay
Yep.
with everybody?
Extra credit.
I will premise it by saying extra credit when it's time. Usually I do. Okay, so I'm going to let that be. Okay. So now, in my opinion, when we go to graph logs, it's easier if we choose values of the y value and then find the corresponding x value when we go to graph log functions. Okay? Hopefully we can get an example. Let's try to get an example going. I'm going to let these be for right now. I'm going to let that be. Okay. So we're asked to graph this, right? I'm going to kind of walk you through this one. So let's start by getting a copy of the original. It's like they're having so much fun over there. Okay, let's get a copy of the original. So, and we have this f of x base 1/2. So now, to graph this log, let's write this log as an exponential. What were we doing before to write these logs as exponentials? What? The 1/2, right? What do we do with the 1/2? Right, we're going to say the 1/2 to the power of y. We're going to swing the 1/2. So we're going to rewrite this log as an exponential, and we're going to get the same result. So this is going to give us 1/2 to the power of y is going to be equal to x. We're going to graph this, right? So let's make a table. So we have our x's and our y's. So now, what you see at the bottom of the screen, would it be easier to choose values of x, or would it be easier to choose values of y in this context? Okay, so for instance, say x were 3, what value of y would make x 3? You see how that can be a little dicey? Right, so instead of choosing values of x here, let's choose values of y. So we're going to choose the y. We're going to go -3, -2, -1, 0, 1, 2, 3. I just chose 3. What's the value of x? So when y is 3, we're going to have what? 1/2 to the power of what? 3. What does that mean? 1/2 times 1/2 times 1/2, which is going to be 1/8, right? So when y is 3, let's do like this. So when y is 3, the corresponding x value is 1/8. When y is 2, what's the corresponding x value? So if y is 2, the corresponding x value is going to be 1/4. When y is 1, what's going to be the corresponding x value? 1/2, okay? When y is 0, what's the corresponding x value? 1, okay? Notice how the numbers are behaving. When y is a -1, what does a negative exponent mean? It flips, right? It flips. So when y is a -1, that 1/2 becomes 2, right? So what's that? So it's going to be a 2 there. When y is -2, what's the 8, right? Because the negative exponent causes it to flip. So then we're going to have 2 to the power of 3, which is going to be 8. So we chose some y values. We found the corresponding x values. Let's plot these on a graph. So we're going to go here. We get out at 1:30. I am watching the clock, so it's okay. X goes from 0 to 10. Y goes there. So we're going to focus on this window. Okay. Oh, no, they want that. Nope. Okay. Oh, and actually, let's do like this. So x's, we're going to go, let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the positive x. Y, we need to go 1, 2, 3, 4 is good. 1, 2, 3, 4 is good there. Here's the positive y. Okay. All right, so let's plot these points. So when x is 8, 1, 2, 3, 4, 5, 6, 7, 8. Y is -3. Yeah, okay. Yeah, let me see. 1, 2, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8. We go down 3 and we're about here, right? When x is 4, 1, 2, 3, 4, y is -2. So we're about here. Oh, the first one was too low, right? Let's clean that up. Redo that first one. So when x is 8, 1, 2, 3, 4, 5, 6, 7, 8, we go down 3. So it's more so like this. Okay. When x is 2, we go what? Down 1. We're here. When x is 1, we're at 0. When x is 1/2, we're at 1. So we're about here. When x is 1/4, we're at what? 2. So we're there. When x is 1/8, so really, really close to 0, we're at 3, so on and so on. So notice we still have this kind of thing going on. So this is a log function, so we do have a vertical asymptote. If we connect these points with a smooth curve, we'll get something kind of like this. All right? So we get a graph like this. It'd be nice if I can keep that. I don't know how to advance it without getting the words to pop up. Okay, since we're doing a video recording, I'm gonna go ahead and clear this ink. And let's look at it. So now the original is the f of x equals log of a half, log of x base half. Written as an exponential was, oh, they're using the inverse. Okay. Well, okay, so we'll get the same kind of thing. So you see our graph in blue. They use the exponential, then they rotate it about the line y equals x, so they just switch the x and the y's, and they got the blue. But you see they get the same blue graph that we got, all right? So the blue was the final result there. Okay, graph this one. Let's do one more really quickly. So to do the same thing, just for some practice. Okay, so here's a copy of the original. Then this is the same as y equals log base 3 of x. So if we write this as an exponential, we're going to get 3 to the power of y equals x. Let's make a table. So we have x and y's. Let's choose values of y. We're going to go -3, -2, -1, 0, 1, 2, 3. I just chose those. So when y, okay, let's work backwards again. So when y is 3, what's the result there? What's our x? So 27, right? Because we have 3 to the power of 3 is 27. Let's do this. Let's do like this. Let's do this one, this. I'm going to change that color. So when y is 3, x was 27. When y is 2, what's our x? 9. When y is 1, what's our x? When y is 0, and 3 to the power of 0 is 1, right? Any non-zero number to the power of 0 is 1, right? So 3 to the power of -1, what is that one? 1/3, right? That's 1 over 3. What's 3 to the power of -2? What is that one? 1 over 9, and 3 to the -3 is 1 over 27. So let's plot these really quickly. X's go from like 0 to 27, y's. So we're going to go 0 to 10, and then -3 to 3. So we're going to go something like this. X's need to go to about 10. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is the positive x. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the origin, -1, 2, 3, 4, 5. So I did my best to draw, to scale as best I could. Okay, so now let's plot these. I'm going to skip to 27. When x is 9, y is 3. So we get a point about here. When x is 3, y is 1. So we get a point about here. Let me think about this. Yes, okay. When x is 1, y is 0. When x is a third, we're at -1. A ninth, we're at -2. And then it just kind of keeps getting closer and closer. So we do still have our asymptote. If we connect this with a smooth curve, we'll get something like this. So that's the graph of, that's the general form of the graph of a log function. It looks something like this. There's a vertical asymptote. Below the x-axis is really close to the asymptote, and then going above the x-axis, it rapidly goes off to the right. This is the general form of a log function. Any questions on how we did this here? Do we need to kind of back up and redo? Any questions here? Okay, so we have enough, right? That's enough for us to kind of talk about there. Let's kind of keep it going. Okay, so I'm looking at the numbers. I'm going to go ahead and clear this ink. Right, so we essentially get the same graph. Okay. Quick recap, and let's do like this color. if this is the general graph of a log function, this is like y equals log of x. If that's the general form of the general graph of a log function, now what we're going to do here, we're going to use that general form to graph, we're going to use transformations to graph this function, right? So if in general we have a vertical asymptote, it passes through 1, 0, I'll give extra credit for this question. What's the transformation going on here? Is it Clement? Okay. Is everybody okay with that? Notice, we subtracted a 1 on the inside of our function, so that is our inside manipulations, are they vertical or horizontal? Inside manipulations, are they vertical or horizontal? So remember, we just subtracted a 1 on the inside. Which way did it move, Ms. Clement? It moved to the right, right? So if it moves to the right, is that a vertical change or a horizontal change? That's horizontal, right? So vertical manipulations or horizontal manipulations. Do the horizontal manipulations, does it follow our intuition or is it the reverse of our intuition?
Reverse.
It's the reverse. I like that. It was very resound. It's the reverse of our intuition, right? So instead of going left 1, it actually goes to the right 1. I'm just trying to recap transformations because we only get that in this course. Okay, so it should be this green graph if we move it to the right. Just go ahead and silence it. If we move it to the right by 1. So instead of the vertical asymptote being on the x-axis, it's going to go through x equals 1. I'm going to clear this out. Yep, this is fine. This is fine. Yeah, right here, right? So notice it's still the same graph. We just moved it to the right by 1. Any questions here? We use transformations to graph this one. We took the general graph of a log, which is essentially what you see on the screen, and we just moved it to the right by 1 using transformations. Okay, let's kind of keep it moving. Okay, I'll give extra credit for this one. So I know we got at least 1 extra credit. Somebody that has not gotten points, what's the transformation going on here? Is that -1 inside or outside of our function? You were too slow on the draw. But you got points already, right? No, you haven't. Okay. So she noticed that so Ms. Benacourt Farias noticed that it was outside our basic function. Are outside manipulations vertical manipulations or horizontal manipulations? They're vertical. Does it follow our intuition or is it the reverse of our intuition? So outside actually follows our intuition. So if we subtract 1, it goes down by 1. So we can follow the point 1, 0. If we look at the graph, it's going to be the same graph, but we moved it down 1, right? We moved it down 1. So that's Ms. Benacourt Farias. Okay. You got it. I was trying to bait you. It's like I was looking for the hand. She got hers up before you. I was watching because I already knew I was going to extra points on this. I got yours. No, yeah, I got you, Ms. Clement. I got you. We're going to keep it going. All right, so let's keep it going. Okay, here's another one. First person to give me the correct transformations. Okay, Mr. Wardrobe, you're on the chopping block. I'll give you a hint. I'll give you a little bit of heads up. There are 2 transformations going on here. What are the correct 2 transformations, Mr. Wardrobe? Go ahead. You can get help. Go ahead.
It goes to the right 2 and then up 1.
I got you.
No, you were next. I was already peeping. You. Miss Rodriguez, right? It's okay. It's okay. It's okay.
Inside is reverse.
Yeah, plus the positive x usually goes to the right. So this actually goes to the left 2 and then up 1.
I just told you why I got it wrong.
It's okay. It's okay. We got to keep it moving. Let's keep moving so we can try to get these points out. Okay, so we got a good amount of points out there. Let's try to get some more. So now, this is still just a regular graph, the regular log function with the vertical asymptote going off to the right. We can kind of follow the vertical asymptote and the point 1, 0. So this graph should go left 2 and then up 1. And then that'll give us what we need. So we went left 2 and up 1 and we see that there. Okay, so that's okay. Let's keep it going. Let's keep trying. That was Miss Rodriguez. She was like, in for the steal. I was like, don't mess this up because you know the points are gonna go away. The thing about opportunities don't go away. They typically go to who's next. That's usually how that goes. That comes from one of my mentors. Now let's see. Sums, quotients. Okay, let's see this in action. Okay, so we have these following properties. We have these following properties of logs, right? So the first one is called the product property. When we take the log of a product, we can rewrite that as the sum of the logs. So the product property is the log of the product can be rewritten as the sum of the logs. So if the log of the product is the sum of the logs, any guess as to what the next one might be? If this is the product property, what do you think the next one might be? Okay, so quotient property. How might a quotient property go? If the product property is the log of the product is the sum of the logs, how might the quotient property go? The log of the quotient is the difference of the logs, right? Okay. Those are three properties of logs that we're going to use to solve log equations. Or simple, yeah, let's kind of look at it. And some other properties of logs. The log of 1 is 0, right? The log of a base a is 1. What have we talked about today that can kind of back up that log of a base a equals 1? What did we talk about today that verifies that? For instance, if we did the log of 3 base 3, how would we put that in the calculator if it was the log of 3 base 3? If it were log of 3 base 3, if we wanted to put that in the calculator, we would do what? Change of base. We would do the log of 3 divided by the log of 3, right? So if we have the log of a base a, that's the same as the log of a divided by the log of a, which is 1, right? That's just using the change of base formula to verify, or I'm kind of at a loss for words right now, but it verifies that property. Okay, we're going to let that be. Okay, I'm going to let that be. Rewrite each expression. Assume all variables represent positive. That's supposed to be multiplication. Okay, so we have a little bit of a typo here. This right here, that's supposed to be multiplication, right? So let's just rewrite it properly. So the original is actually supposed to be log base 6 of 7 times 9. How can we rewrite this? What was the product property again? This is the same as what? Log property that we just said.
It's gonna be you're gonna add it.
Right. We can rewrite it as the sum of the logs, right? So this is the same as the log of 7 base 6 plus log of 9 base 6. Let me think about this. Okay, I'm gonna let this be. I don't see where they want us to do anything more. Yeah. So that's it. Oh no. Okay, so that was it there, right? Again, that G was supposed to be multiplication. That's a typo, but then it becomes, so the product of the logs, the log of the products becomes the sum of the logs. So what does this one become? Difference of the logs, right? So it becomes log 15 base 9 minus log 7. Okay. What about this one? What's the exponent here?
You would just have to it's 1/8.
Not 1/8. 1/2, right? This is square root. Because it's square root, it's to the power of a half. So then this is going to be the same as a half times log of 8. Because the square root of 8 is 8 to the half. The half can essentially just go in front. So this is just a property that we just introduced like a few minutes ago. I want to try to wrap this up. We got about 20 minutes remaining. Okay. I want to wrap it up in the next 10 minutes. I think we can finish in the next 10 minutes. We have just outside of 10 slides remaining. Okay. Let's keep it moving. Rewrites. All right. To somebody that has not gotten extra credit, if you want to team up, that's fine. First person to give me the correct result here, I'll give you extra credit for this one. You got it ready to go?
Yeah.
Okay. Tell me what to write.
It's 2/3 log AM. Log M.
Base A, okay.
It's crazy.
Okay, I think I can honor that. Okay, I gotta grill you a little bit though. So, now, let's get a copy of the original. We have log base A. We got cube root of m squared. What do we do with that cube root of m squared? That's the same as what? How do we rewrite that part first? Wait. Yeah, so m to the power of 2/3, right? If only we had this kind of like cooperation on the exam, we'd be like blowing it out the water.
Yes.
I knew I shouldn't have said it because I was like, can't put those ideas in your mind.
I'm saying it'll help us.
I mean, honestly,
And your YouTube channel.
I'm just doing the YouTube. I'm just doing that just to be doing it. But honestly, I mean, if it's open notes, that's what we're doing. You know. No, that's not what I'm saying. You can talk to your notes. So if you have stuff pre-worked out in advance, and then it's open notes, I don't mind that. I don't want to do a collab exam. I just don't want to do that.
Okay, we ain't collabing, but say like on her notes, she got something that can help.
No. Everybody's using their own notes. Now, if you work that out in advance, I can't stop that.
Yeah,
But
like,
during the exam live, we're not passing notes during the exam. No live. No, not during the exam. We can just do a closed note exam if that's better. We can do that. We can go that direction. Okay. But again, because it's a quarter system, I don't really mind. I don't mind points here as well. So that was Miss Ingram. Okay.
yeah,
Man,
so
most
I got two, right?
that's only one.
What happened to the other extra credit?
It never was there. We got the video to prove it. It was never anything. Okay, let's keep it moving. So I think that was okay. So cube root of m squared became m to the power of 2/3. The power rule says that the log of the exponent is the exponent times the log. So we're just using that property. Okay. Somebody that has not gotten points. I'll give points for this one. Somebody that has not gotten points.
But no one else wants it, so I'll take points. Oh, okay.
This is only for people that have not gotten points, right, Mr. Wardrobe? Okay. All right, I can get down with this. All right, walk me through it. We're applying several properties here, right?
Plus log base a cubed, and then minus log base a p squared plus log base a t.
Okay, wait. Log base a of p squared. Okay. Keep going.
Log base a t to the fourth power. That's in parentheses.
Okay, that's what I was looking for. Base a of t to the 4. We're almost there. There's another step, right?
And then
So let's rewrite the original because all that stuff was good. This log of n base a plus log of q base a. Okay, now what about the next part?
and then
Yes, I heard.
distribute,
Distribute the negative, right? If we distribute,
and then you get log base a m plus log base a n plus log base a q minus 2 log base a p minus 4 log base a t.
so how did that 2 get out of the exponent? What? Because remember, the first property was the product rule. The second property was the quotient rule, the power property, right? So the log of the exponent becomes the exponent times the log. So then what you said is correct. Negative 2 times the log base a of p. Oh, what is the last one? 4? Nope. I made a mistake. Come on. Nope. Okay, right here. Minus, right? This. Okay. Minus what? 4 log base a of t. I think this is okay. That's a Wardrobe, right? He was able to keep up.
We get a 0.5.
5 points out of 100 for the quarter. So we want to keep trying to get these points going. Hopefully we can maximize our extra credit. If I can apply it, as long as it doesn't skew the grades too much.
So each point is 5 points?
Yeah, every time I give out extra credits in 5-point increments.
So like say if I have a 69, so
Nope. So no. So when you get 100 points extra credit, I'm going to scale that to 10% of your grade. So like if you were to maximize your extra credit to 100 points, that could potentially boost grades by 10 points. So like if you finish at a 72, provided it doesn't skew too many of the grades, then I can boost it to an 82.
How about you just count the points? Like if I have a 69,
It don't work like that. That's too heavy a weight. It's not worth that. No, that's too heavy. That's too heavy a weight.
So, can you tell us how many points we have?
I don't calculate points until the end. I just log them in my system, and I have it on file, and then I go and tally it at the end. So I don't even know. Now, as you accumulate points, it's probably a good idea for you to have the records on your own. I usually tell you guys when I give you points. Go ahead. I haven't applied extra credit to any grade at all. So I've just been recording it all the way. Pardon? Huh? It's just extra credit. So if you don't get it, then the grade is just flat. If you do get it, then it's going to boost it. It should, boost it by something, a little bit.
So we got to get 100 extra credit points to get the extra credit?
To boost the final grade by 10 points.
So I've been busting my bottom for no reason.
So it's a possibility we can boost it by 8.
Got a week in the quarter in.
So, okay, we need to kind of keep moving because we got about just outside of 10 minutes. Let me clear this out. Hang tight because we're almost done, actually. We don't have too much further to go.
He's got to give me my extra credit.
I'm going to give it. Let me just kind of go ahead. Actually, let me see how many slides are left. I'm going to leave this one as an exercise. You definitely want to take a look at this, right? Take a look at it. Make sure it works for you, okay? So take a look at it. It's kind of the same thing, a few tweaks or whatever. Let's do this one really quickly. Write each expression as a single log. Okay, so this one is working in reverse. They want us to write it as a single log. So we want to work those properties backwards, right? So if we said the log base 3 plus the second log base 3, what happens with those two parts? So which rule is that in the first one? So the first rule said what? The log of the product becomes what? The sum of the logs, right? So if the log of the product is the sum of the logs, then the sum of the logs is going to be the log of the product. We just work it backwards, right? So the first one we can write as log base 3 is going to be x plus 2 times x, right? We still have this guy, minus log base 3 of 2. So now, if the log of the quotient is the difference of the logs, then the difference of the logs is the what? Log of the... So if the log of the quotient is the difference of the logs, then the difference of the logs is the log of the quotient, right? So we can divide these. So that's equal to the first, and then this is going to be basically x plus 2 times x divided by what? 2. We're going to say log base 3 of this thing. And that's going to be the final in 1 come along. So we basically just worked it backwards. We worked it backwards. Let's clear this ink. I'm watching the clock. Yeah, we need to wrap it up. Okay. Yeah, there it is right there. Okay. This is a similar kind of deal, so I'm going to leave this as an exercise. Similar deal. I'm going to leave this as an exercise. You can do it. Takes a little bit of practice. There is no property of logs to rewrite the log of a sum or the log of a difference. So again, we have a product rule which says the log of the product is the sum of the logs. The log of the quotient is the difference of the logs. The log of the power is the power times the log. But we don't have anything that says the log of the sum. You see what I'm saying? You see the difference? It's very subtle. The difference is very subtle. Do you see the difference? We can break apart the log of the product, but we cannot break apart the log of the sum. Is that okay? Again, what we were given, the log of the product is the first log plus the second log. In this case, we're given the log of the sum. We can't break this apart. We can't break apart the log of the difference, right? So it's very subtle. It sounds like I'm saying the same thing. If you think about it, you'll see the difference, okay? I'm going to leave this one as an exercise as well. You can handle this one. This one we have to use a calculator. I think we talked about this one, right? I'm going to leave this one as an exercise as well, though. I'm going to leave that one for you. So logs and exponentials they cancel each other out, right? So if we say an exponential to the power of a log, they essentially cancel. If we say the log of an exponential, those cancel and we're left with only the exponent. That's what's going on here. The logs and the exponents are cancel each other out. So you're going to have to take a look at that and do the best you can with it, okay? So on that note, let's go like this. on that note, we're going to end this session here. Okay, so hopefully that wasn't too bad. So we're going to end here, and from one beautiful mind to another, enjoy the rest of your day. Give me just a moment.